I'm going to discuss Parseval wavelet frames on Vilenkin group, but not only on Vilenkin groups. The main results I'm going to present will be for two situations, on Vilenkin group and also on semi-line, positive semi-line of one-dimensional Euclidean space. And also Parseval wavelet frames. I'm interested in such frames that are from very good function. It will be clear what means from very good functions. Joint results with Yerevan. What is it Vilenkin group? It is associated with the integer p, bigger or equal to than 2. It consists of sequences of digits, 0, 1, p minus 1, and where only at most finite number of negative j, non-zero xj, such that xj is not 0. And next, group operation, addition. This is coordinate-wise addition modulo p. Of course, minus is also introduced. And as for positive semi-line, also the similar addition. Also similar addition for non-negative numbers. Next, the topology. Topology is introduced by these system of neighborhoods of zero element. Zero element, it is clear what is this, called zeros. And this is a group, hence there exists the Haar measure on group, and mu means normalized measure. And on semi-line, we also introduce the same addition. Next, it will be convenient for us to write elements of the group G, Vilenkin group, as well as we write decimals. Decimals, especially if p is equal to 10. So this is an element, comma here. If x in the neighborhood u, then we write 0, comma, etc. Then is if zeros right to xn, we do not write them. Next, h. H is an analog of integer numbers, integer positive numbers, and I will say these are positive elements of the group. And we can, it is convenient to introduce such lambda of x in the case of this is one. This takes 1 to 1 from z plus to h, 1 to 1 correspondence. But of course, lambda is not 1 to 1 on the positive semi-line. Positive semi-line is not a group with the same addition, but of course it is not a group, even no association for the semi-line. Okay, so one-to-one correspondence. I will write H alpha like this, positive element of the group. Next, we need automorphism A. So we can compare with positive numbers with semi-line. It is just actually multiplying by p, and this this neighborhood corresponds to the interval on the positive semiline, and also we need we need sets U and S which are analogs of these intervals. And next we introduce step functions. Step functions, class Sn is a class of functions that are constant on all these sets. And S, N, L, the set where F in this class and also supported in A, L, U. And this, why we're interested in this class of functions, because a little bit later it will be clear that these are very, very good functions. Very good functions. Next, Vilenkin group is group, so we have characters. Characters are given by explicit formulas. More precisely, for fixed omega, he of x is a character. Standard properties of characters, and characters and the notion of Fourier transform is based on the characters standard way. This is definition of the Fourier transform. I will discuss only Vilenkin group now in general facts about Vilenkin group, and as for semiline, similar transform and everything similar are known. There were a paper by my co-author Farkov and Vladimir Protasov, so a lot of similar things. Now, important theorem. F belongs to class, step function, and compactly supported function. F belongs to this class if and only if its Fourier transform belongs to this class. And now it is clear why functions from this class are very good functions, because it is an analogous Schwarz class. What we want to have from functions, we want the functions to be smooth as possible, and decay as small as possible. And the best decay is compactness of the support. And in usual analysis, in usual harmonic analysis, it is not possible. The function itself and its Fourier transform are compactly supported. And here on Vilenkin group, it is possible. So both functions, f and f hat, are compactly supported. Okay. Next, Walsh functions. Walsh functions are characters with integer second component, and this Walsh function H periodic, which means this for integer H. And the Walsh function form an orthonormal basis for L2 on U. So we see that this function analogs of usual of harmonics in usual analysis. And linear combinations are called Walsh polynomials. This linear combination is Walsh polynomials of order n, and this class of Walsh polynomials of order n such that m0 from 0 element is equal to 1. A function is Walsh polynomial of order n if and only if it is H periodic and belongs to Sn of G. From here it is clear that Walsh polynomial of omega, of element omega, can be written like this: 0, comma, and then only one components. Next, about wavelets. I have discussed wavelets. What is it, wavelet system on the Vilenkin groups? As in usual analysis, they are generated by a finite number of functions, wavelet functions, and consist of dilations and translation of this function. And system, wavelet system psi here on psi is called Parseval wavelet frame is if this holds true for all f from L to of J. It is clear that this is generalization of the orthonormal basis. Parseval wavelet frame. And next, construction of Parseval wavelet frames is very similar to usual analysis, real analysis, standard analysis. It is based on refinable function. This is definition of the refinable functions. Next, I will miss this. No, I will not miss. Phi is compactly supported if and only if the sum here is finite. So we are interested in compactly supported refinable functions, so we will consider this refinement equation. And taking Fourier transform, we see refinement equation in the Fourier domain. It looks like this, more or less the same in usual analysis, in the real setting. And here, these are Walsh polynomial. In usual analysis, these are trigonometric polynomials. M0 is called mask, the mask of refinable function f. And if phi is compactly supported refinable function, that phi hat is the infinite product. And if moreover M0 in that class, then this factor is 1, and it is just finite product of mask this, just explicit. Next, it was known how to construct compactly supported. Step 1, we take appropriate Walsh polynomial. Appropriate means these conditions are satisfied, and it is very easy to satisfy this condition, just small amount values. M0, Walsh polynomial, is defined by finite number of values, so they should be small enough. Next, phi hat is infinite product, which are actually finite product. Next we define wavelet masks, such a Walsh polynomial that the matrix, this matrix is an orthonormal. The rows of this matrix form an orthonormal system. How they may be found, it is known. There is, in our paper, there is an explicit method to find. And when we have these functions, we have wavelet functions. And this is to construct compactly supported refinable function. But we need not only compactly supported, we need to have step function. From here, it is clear that if phi is a step function, that wavelet functions are also step function. So our goal to provide not only compactly supported phi, but also step function. And there were some examples in the paper of my co-author Farkov and in some other paper. But how they appear is not clear. Just just fall down from the sky. Oh, this is a good example, step function. And our goal was to describe all compactly supported step definable functions. We need a definition, the following definition, given Walsh polynomial M0, we denote by sigma n the set of vectors S1, etc., Sn, consisting of digits, such that for any subchain, subsequence consisting of n small n elements, this is non-zero. So in this case, we say this, the set of all such vectors is Sn. And this is the main result. Let M0 is a Walsh polynomial in this class, and let capital N is equal to this. For M0 to be a mask, the mask of a compactly supported definable step function, it is necessary and sufficient that this sigma n to be empty. How to describe all such functions? We take an arbitrary chain of digits. So it should be such that there exists at least one subchain consisting of n elements that vanish M0. Let us look. This is the case P equal to 3, N equal to 3. So capital N is 8. We can draw a tree to see all sequences. Of course, this is only a small piece. It go right, and right. More 4 or 5 columns should be to get capital N equal to 8. But what we need each branch of this tree should contain an element that vanish M0. The simplest way, way to organize this, to implement this vanish and this vanish. Then, obviously, all branches has a vanishing element. If this does not vanish, instead, we can require this 3-element vanish M0. If not, and when we look at this column, not necessary to vanish this element 1, because after this element, what we have 1, 1, 0, 1, 1, 1, and 1, 1, 2. But this is the same as these 3 elements. And every element in circles, it's okay, we should not take care, so it remains this 5 or 6 elements, and then we continue. So there are many ways to implement each branch contain vanishing element. This example for P equal to 3 and N equal to 2. For the N equal to 2, only capital N is equal to 3, and here it is possible to present all possibilities. First possibility, first column vanish, B is just value of M0. And in this case, we have characteristic functions. Next situation, this is 0, but 0, 2 does not vanish, and instead we have 3 vanishing elements in the next column. It looks like this. Similarly, here 5 zeros, 5 vanishing elements. Phi hat looks like this, and phi looks like this. So all cases are vanished explicitly. And next, a general theorem for n equal to 2 and arbitrary p. So let M0 in this class and n and let C1, etc., CR be a vector consisting of different elements and non-zero elements from 1 to p minus 1. Non-zero digits. Suppose M0 vanishes at each point 0, S prime, where S is non-zero, and this is not a pair from this sequence. Then M0 is the mask of a refinable function from this class. So this is step function with the corresponding size of step. And all this to construct Parseval-Wavelet frames, but special case of Parseval-Wavelet frames are orthogonal, orthogonal wavelets, orthogonal wavelet systems, and under the same assumptions, if we additionally suppose this is modulo of this value is 1, and modulo of these values are 1 for such S, and M0 of 0, Xi chi is 0, then M0 is the mask of an orthogonal refinable function of the same class, and the corresponding wavelet system is orthonormal wavelet basis. Thank you.